Dear students, I welcome you all in the lecture series for GATE 2021 under Prerana scheme of AICTE. So in the previous two lectures, we have discussed about the basic terminologies that were used in thermodynamic analysis, and we have discussed work interaction in various processes. And in the last, we have discussed about ideal gas, its properties, and when steam is considered as an ideal gas. So the conditions we have discussed. So now in this lecture, that is the lecture number 3 of classical thermodynamics, we will continue with energy interaction. In the previous lecture, we have discussed about work interaction. Now in this lecture, we will discuss heat interactions. And at the last, we'll discuss the first law of thermodynamics and its consequences. So let us define the term heat. Heat is defined as energy in transit. Basically, in early 19th century, it was thought as an invisible fluid and called as caloric that flows from warmer body to cooler ones. So it was a conception in previous time, and they consider heat to be something like fluid that will flow from a hot body to a cold body, and they call it as caloric. Now, as far as the thermodynamic analysis is concerned, the only two forms of energy interaction associated with a closed system are heat transfer and work transfer. So, work transfer and work interaction were discussed in the previous lecture, and in this, we are going to discuss heat interaction. So, an energy interaction is heat transfer if its driving force is temperature difference. Suppose there are two bodies, there is a temperature difference, then heat will flow from a body at a higher temperature to a body at a lower temperature. Okay. So basically, it is a spontaneous process. In daily life, we frequently refer the sensible and latent form of internal energy as heat, and we talk about heat content of bodies. However, as far as the thermodynamics is concerned, we refer them as thermal energy to prevent any confusion with heat transfer. Heat is also defined as the form of energy that is transferred between two systems or maybe a system and its surrounding by virtue of temperature difference. That is, an energy interaction is heat only if it takes place because of a temperature difference. And it can be concluded that if there is this equilibrium thermal, then heat transfer will not going to be take place. Now, in work transfer, force was the driving agent. Okay. Now, in heat transfer, temperature difference is that driving force. The larger the temperature difference is, the higher is the rate of heat transfer. As you can see on the screen, that the bottle number of soda is at 25 degrees Celsius, and the room air is also at 25 degrees Celsius. Then here there will be no heat transfer taking place. In second case, there is a temperature difference. The soda bottle is at 15 degree Celsius and the room air is at 25 degrees Celsius. So you can see that heat transfer is taking place at the rate of 8 joule per second. Okay. Now, if I further lower the temperature of this soda, if I bring it at temperature of 5 degrees Celsius, then you can see that the rate of heat transfer will increase. Okay. So as the larger is the temperature difference, the higher is the rate of heat transfer. Now, let us discuss about an adiabatic system. Okay. So you can see on the figure that our system, which is marked by the red dotted line as its boundary, is an adiabatic system facilitated by some insulation. And in an adiabatic system, you can see that there will be no heat interaction taking place. In such processes in which there is no heat interaction are termed as adiabatic process. So during an adiabatic process, a system exchange no heat with its surrounding. Okay. So heat interaction is not there in an adiabatic process. So the word adiabatic comes from the Greek word adiabatos, which means not to be passed. A process can be adiabatic in two ways. Either the system is well insulated so that only a negligible amount of heat can pass through the boundary, or both the system and the spring are at the same temperature, and therefore there will be a driving force like temperature difference for heat transfer, or the process will take place. Now, there are generally three mechanisms of conduction, convection, and radiation. Although during a heat transfer process, all of them, or at least two of them, are in practice or working at the same time. So, conduction is basically a heat transfer mechanism due to collision of molecule. Convection is a special case of conduction, that is conduction at the surface and density difference. And due to density difference, the heat transfer will be continued. Okay. And radiation is electromagnetic wave emission. So heat transfer will encounter simultaneously all the three modes or any of two also. So the amount of heat is called specific heat. So you can see on the screen that this 1 kg iron block, okay, will get a temperature difference by getting 4.5 kilojoule of heat. Okay. And to raise the same temperature of water, 41.8 kilojoule of heat is required. So from the figure, it is evident that different amount of energy required to raise the temperature different substance by same amount. The temperature rise of iron is also 10 degrees Celsius, and the temperature rise of water is also 10 degrees Celsius. So you can see in case of iron, the amount of heat required is 4.5 kilojoule, but in case of water, it is 41.8 kilojoule. So large amount of heat is required to raise the temperature of water as compared to iron. So different substances require different amount of energy to raise the temperature by the same amount. Okay. Now let us define the specific heat. As I already told, that specific heat is the energy required to raise the temperature of a unit mass substance by 1 degree. Okay. Now, this energy depends on how the process is executed. Okay. So, previously we have discussed variety of processes, whether it is constant volume, whether it is constant pressure, whether it is isothermal, whether it is adiabatic, whether it is polytropic. So this energy depends upon the execution of the process. Basically, as far as the thermodynamic analysis is concerned, we are interested only in two types of specific heat. That is specific heat at constant volume and specific heat at constant pressure. Specific heat at constant volume is referred as CV, and specific heat at constant pressure is referred as CP, as you can see on the screen. So you can get an idea that there is a block having mass 1 kg and the change in temperature is 1 degree Celsius. Okay. So the specific heat is that amount of heat required by this particular element to get an increment in its temperature by 1 degree Celsius. So here it is 5 kilojoule per kg per degree Celsius. So the unit is kilojoule per kg per degree Celsius. So I will discuss about the units in further slides also. So you can see that in this example that different substances require different amount of energy to raise the temperature by same amount. Okay. And in the upcoming slide, you can see that if the temperature difference is same and if this material is also same, but at different temperature, to raise this amount of temperature require different amount of energy. Okay. So we'll see that specific heat is a function of temperature also. So as I discussed, the specific heat at constant pressure and specific heat at constant volume is of interest as far as the thermodynamic analysis is concerned. In the figure number 1, you can see there's some element is there having mass 1 kg. Okay, some sort of gas is filled in this chamber. The volume is constant and there will be an increment of 1 degree Celsius. So if I supply heat, the amount required is 3.1 kilojoule per kg per degree centigrade. But if the process is not constant volume, if it is constant pressure, if I allow the piston to move and if I am supplying the heat, then the amount of energy required is a little bit more. You can see that the specific heat at constant pressure is more than the specific heat at constant volume for same configuration. Here the process is constant volume and here the process is constant pressure. So I will give you an idea that why such kind of energy is required here. So some part of this heat some part of this energy is being utilized by this gas in lifting this piston to make the process constant pressure. So you can see, if you want to make this a constant pressure process, okay, so some amount of energy is required by this gas to lift this piston, and that energy is expended as a work in lifting this piston. That's why specific heat at constant pressure is more than specific heat at constant volume. Okay. As there is no work required in lifting anything. So the amount of energy that is being imparted to this gas is fully utilized. But here, some of the part of the energy is utilized in lifting this piston. That's why here we require more energy. So here you can see the specific heat at constant volume in differential relationship. That is the change in internal energy with temperature at constant volume. Okay. So CV is associated with change in internal energy. Okay. And CP is associated with change in enthalpy. As here the motion of piston is associated, that's why we have encountered the term enthalpy. I will tell you, basically enthalpy is nothing but a combination of internal energy plus flow work. So it is just an index or just a combination of two terms. Okay, that is internal energy and flow work. You can see the specific heat at constant volume is associated with change in internal energy, and the specific heat at constant pressure is associated with change in enthalpy. And enthalpy is nothing but the combination of two terms, that is internal energy and flow work. Okay. So I hope you get the idea what is specific heat, what is specific heat at constant pressure, what is specific heat at constant volume, and why the value of Cp is greater than Cv. Okay. So physically, I have explained it, and we can also mathematically derive it. Now, I will tell you another aspect of specific heat, which I was telling you earlier. If I want to raise its temperature by 1 Kelvin, so the amount of energy required to do so is called specific heat. So here the value is 0.718 kilojoule. Okay. So but in if I take same configuration, but if my initial temperature was 1000 Kelvin, and if I want to raise the temperature to 1001 Kelvin, that is by 1 Kelvin, an increment of 1 Kelvin. Here also the temperature difference is 1 Kelvin. Here also the temperature difference is 1 Kelvin. But you can see that the amount of energy required to do so is different. Okay. So it is another aspect of specific heat, that specific heat changes with the value of temperature also. So specific heat is a function of temperature. At different temperature, to raise the temperature by same amount of same material, we required different amount of energy. So specific heat is a function of temperature. But for a temperature range, we will consider an average of that value. Okay. We will not define specific heat at each and every temperature, but for a range, we will consider an average value of specific heat. You can see here on the diagram. that it is the diagram between specific heat at constant pressure and temperature. Okay, so at temperature T1, the specific heat required was this, and at temperature T2, the specific heat required was this. So for this range, we can consider it the average value of specific heat. Okay. And we can consider its variation to be linear. Okay, for small temperature intervals. Now, a common unit for specific heat is kilojoule per kg degree centigrade or kilojoule per kg Kelvin. As in the first lecture, I told you that change in degree Celsius is equal to change in Kelvin. So, in place of degree Celsius, you can also write as Kelvin. So, if in numerical some sort of units are given, then don't be get confused because it will not alter the answer. Okay. Now, the specific heats are sometimes given on the molar basis and are denoted by a bar on that CV or CP. Okay, and the unit is kilojoule per kilomole degree Celsius or kilojoule per kilomole Kelvin. Okay, so we have seen that specific heat is also a function of temperature. But for sake of convenience, for a range of temperature, we will consider an average value of specific heat. Now, before proceeding to the internal energy, I would like to give you an insight of what internal energy is. So you can see on the screen the various forms that are associated with internal energy. Okay. So how a system's internal energy is and how can you visualize it? So molecular translation. Okay. The molecular translation, molecular rotation, electron translation, molecular vibration, electron spin, nuclear spin. So all these are associated for internal energy of a system and are responsible for an internal energy of system. Okay. So these are the various microscopic energy that sum up and can be called as the internal energy. Okay. So you can see sensible and latent energy, chemical energy, nuclear energy. Okay. If you bifurcate it, or you can also called it in this manner also, that these three forms, that is sensible and latent, chemical and nuclear energy, together constitutes internal energy of system. Okay. And sensible and latent energy is nothing but this molecular translation, rotation, and all these things. So this is what the internal energy is. And these are responsible for internal energy of anything. Okay. Now let us discuss Joule's experiment. Okay. So Joule was the one who gave a fundamental relation that the internal energy depends only on the absolute temperature. So he created a setup in which he filled water and placed two chambers, one with high air pressure and the other chamber is evacuated. Then and there is a valve and there is a thermometer to assess the temperature of this water bath. Okay. When he opened this valve, okay, and when the constant pressure and constant volume condition reached, he find out that there will be no increment in the temperature. So he concluded that the internal energy depends only on temperature. It does not depend on pressure. It does not depend on volume. And mathematically, it can also be proved that internal energy is a function of temperature only for an ideal gas. Okay, we are talking about ideal gas. This was the setup of Joule, with the help of which he gives a conclusion that internal energy depends only on the absolute temperature. It is not the function of gaseous volume. So I told you that enthalpy, H is enthalpy, is an index or sum of two properties, that is internal energy, which I have defined here, that these constitutes internal energy of any system, and PV is nothing but flow work. Okay. From the ideal gas equation, we know that PV is equal to RT. Okay. Here V is specific volume here. So in place of this PV, if I write RT, then H becomes U plus RT. Okay. Now, what is the significance of this equation is, from this you can say that since U is a function of T, okay, R is a constant and T is temperature. So H is also a function of temperature. Enthalpy is also a function of temperature. So this was the Joule's experiment, and he gives Joule's law, which states that the internal energy is a function of absolute temperature for an ideal gas. Okay. And he determined the constant of proportionality to be a specific heat. We will discuss it in the further slides. So the constant of proportionality for the Joule's law came out to be Cv. Okay. So U is a function of T, and U is proportional to T. U is equal to CVT, or change in internal energy is equal to CV delta T. So this was the equation given by Joule's, that is delta U is equal to CV delta T. Okay. So you can see from the example that we have taken a closed chamber where volume is constant and our system is ideal gas. We have considered air, and we supplied heat, and the temperature get increased to 30 degrees Celsius. So there will be a change in the internal energy of the system, and it came out to be 7.18 kilojoule per kg. Okay. Now if I change the setup, okay, and convert it into a constant pressure process, then you will be amazed that delta U will be same. So delta U is equal to CV delta T is valid for any kind of process, whether it is constant volume or whether it is constant pressure, any kind of process, this relationship is applicable. So now let us proceed our discussion. So from the Joule's law, it is evident that internal energy is a function of temperature, and we have derived enthalpy as also a function of temperature. Specific heat, as I already told you by an example, that is function of temperature, but we will consider an average value. Okay. For an ideal gas, U, that is internal energy, enthalpy, specific volume at constant pressure, and specific heat at constant volume vary with temperature only. Now let us see the specific heat relations for an ideal gas. Okay. So special relationship between Cp and Cv for ideal gas can be obtained by differentiating the relation which we have derived, that H is equal to U plus RT. Okay. Then it will become dH is equal to du plus R dt. Okay, and we know that dH is nothing but Cp dt and du is nothing but Cv dt. And if I replace them, it will become Cp is equal to Cv plus R. Okay, or Cp minus Cv is equal to R. So by this, you can get the relation between specific heat at constant pressure and specific heat at constant volume. And I already explained it physically that how specific heat at constant pressure is more than the specific heat at constant volume. Okay. So this is an important relationship for an ideal gas since it enables us to determine Cv from knowledge of Cp and the gas constant R. So if molar relations are, you can also calculate using universal gas constant. So I hope the specific heat relation for ideal gas is clear, and we have derived Cp, Cv, and R units. Cp minus Cv is equal to R. Now let us proceed. Now we'll discuss about the internal energy enthalpy and specific heat of incompressible substance, that is solids and liquids. Okay. Till now, we have discussed about internal energy, enthalpy, and specific heat of gases. Now we'll discuss about internal energy, enthalpy, and specific heat of incompressible substance or solids and liquids. Okay. So we'll assume here that liquid is also incompressible. Okay. So substance whose specific volume or density is constant is called an incompressible substance. Okay. So for an incompressible substance, we are not having Cv and Cp. Okay, we are having only value that is C. So the Cv and the Cp values for incompressible substance are identical and are denoted by C only. So we will not use the prefix like Cp and Cv. We will just denote them by a singular function that is C. Okay. Now, like those of ideal gas, the specific heat of compressible substances depends on temperature only. Okay. So you can see the partial differential equation defining Cv. Okay. And although it can be replaced by ordinary differential, and the result is this du is equal to Cv dt. Here we have to use the average value as I already told you that the specific heat is a function of temperature. So let us proceed. So this is the enthalpy change. Okay. So I already defined what enthalpy is. It is just a combination of two things, that is internal energy and flow work. Okay. And you know that V is constant. Okay. So when you solve this differential equation, that dV becomes zero. Okay. And the equation will turn out to be dH is equal to du plus VdP. And when you integrate it, you will get del H is equal to C average del T plus V dP. Obviously, the unit will be kg, kilojoule per kg. So for solids, the terms V delta P is insignificant. Okay. And thus delta H is almost equal to C delta T. And here we are going to take C average. And for liquid, two special cases are commonly encountered. One is constant pressure, that is in heaters. Okay. And one is isothermal or constant temperature process, that is in pump. So it is about the internal energy, enthalpy of compressible and incompressible substances. Now, let us come to the ending part of the lecture, that is the first law of thermodynamics. Okay, so I am proceeding it in some different way that you can correlate it with the law of conservation of energy. So, energy balance for any system undergoing any kind of process can be expressed as, obviously, energy in minus energy out is nothing but the change in energy of system. Okay. So, this term will represent net energy transferred either by heat or by work or by mass. And it is the change in internal kinetic potential energies. Okay. And if you want to convert it into rate form, you have to put a dot here. It indicate it in rate forms. So from this, I will come out for the first law of thermodynamics. And the statement is that for a closed system undergoing a cycle, the net heat transfer is equal to the net work transfer. Okay. For a closed system undergoing a cycle, the initial and the final states are identical. Okay. So if the initial and final states are identical, then the change in energy of a system will be zero. Okay. Then the energy balance for cycle simplifies to energy in is equal to energy out. And a closed system does not involve any mass flow across its boundary, as we have discussed in closed system, open system, and isolated system analysis. The energy balance can be expressed as W net out is equal to Q net in, or in rate form, it can be represented by putting a dot. So for a cycle, the net heat transfer is equal to net work transfer. So it is the statement of the first law of thermodynamics undergoing a cycle. So these are the generalization. Okay, that is Q minus W nothing but change in energy. And for stationary system, we are not having, or the change in the potential and the kinetic energy are almost negligible. So it came out to be Q minus W to be delta U. And on per unit mass, you can also define it, and in differential form you can define it. Now there are certain consequences or the corollaries of the first law of thermodynamics. So we'll discuss this. I think that my screen is not visible. So basically, there are three corollaries or consequences of the first law of thermodynamics. The first one is that the perpetual motion machine of first kind is not possible. So perpetual motion machine is a hypothetical machine which gives continuous output of work without consuming any energy. The first law say that such sort of device is not possible. It is impossible to develop a perpetual motion machine of first kind, as it is associated with the first law of thermodynamics. We are calling it as PMM1. Okay. Now, the second corollary, which we have already seen, is that delta U is equal to Q minus W. Okay. So the change in internal energy, or in the broader sense, you can say the change in energy is Q minus W. The third one is the energy of an isolated system is constant. We have already seen this. These are the three corollaries of the first law of thermodynamics. So before ending the lecture, we will discuss certain points. Okay. Now I think that the screen is visible. So till now we have discussed about work and heat interaction in various processes like isochoric, that is constant volume, isobaric, that is constant pressure, isothermal, that is at constant temperature, that adiabatic, and polytropic. So we have discussed heat and work interaction in various processes and PVT relationships. Now I will share something from gate point of view. So as the time is limited, we will discuss the previous year gate questions on the topic that we have discussed in lecture number 2 and lecture number 3 in next class. In first lecture, we have already done 10 previous gate year questions. In lecture number 2, we have done 3 or 4 questions from gate. So there are more questions associated with work transfer. And in today's lecture, that is, we have discussed heat interaction and first law. So some questions which were left in second lecture, and the questions which were left in the third lecture, we will continue to solve the previous year gate questions in lecture number 4. Okay. where there is problem in sharing the screen. I will try if the screen gets shared, then I will tell you some important points as far as the gate exam is concerned. The system is hanging. So till now we have discussed about the thermodynamic terminologies, zeroth law, significance of temperature, heat interaction, work interaction in various processes like constant pressure, constant volume, isothermal, polytropic, adiabatic, and we have discussed the first law of thermodynamics, its correlationship with the law of conservation of energy, and the three corollaries of the first law or the consequences of the first law of thermodynamics. My screen is not working. So we'll discuss about the previous year gate question for this lecture in next session. And now I am ending my lecture and will hand over to Professor Chandak to continue with engineering